My name is Hsiao-Yun. Thank you. I'll be presenting our work on evaluating sampling effects on catch rates for the longer survey. So back in the 1970s, the Hudson River Biological Monitoring Program was developed to address people's concern about the potential impact of impingement and entrainment on fishes in the Hudson River. And the longer survey was one of the surveys developed for monitoring abundance and spatial temporal distributions of fishes. Two gears were used in the survey. Epibenthic sled and tuck control were used to target early life stages, including eggs, larvae, and juveniles. So the longer survey was originally designed for striped bass, but over time the species of interest changed. So there were some logistic changes in the sampling design which could result in biased estimates of abundance and spatial temporal distributions. So in this study, we evaluate sampling effects on catch rates for key species, and we'll see what are the changes in the sampling design first. So the first thing we noted is that the survey switched from daytime sampling to nighttime sampling during the year. So the x-axis is day of year, and y-axis is number of sampling events. And the red bars are daytime sampling, blue bars are nighttime sampling. Because the survey was designed for striped bass, so generally the survey started before the beginning of the striped bass spawning season. And three weeks after the occurrence of striped bass eggs, the survey switched from daytime sampling to nighttime sampling to decrease gear avoidance by post-toxic larvae. Even if it was designed for striped bass, the survey start dates varied among years, possibly due to the changes in the species of interest, which we'll see in a minute. And after the spawning seasons of most species, the survey changed from weekly sampling to bi-weekly sampling. And this graph is showing the sampling intensity over space. The x-axis is river kilometer, and y-axis is number of sampling events. So even if the survey sampled throughout the river from the Mount Battery to Albany, the sampling intensity was not even over the river. In early years, the sampling intensity was higher in between river kilometer 50 to 150. In terms of species of interest, in the very beginning, only striped bass was considered as a key species. But over time, more and more species were listed as key species for the survey. And in this presentation, we'll look at striped bass, American shad, and white perch. These three species use the Hudson River Estuary as their spawning and nursery habitats, and they are either economically important or ecologically important species. So we use statistical models to evaluate sampling effects on catch rates for the three species. And we'll start with striped bass. So this is model estimated peak season for the three life stages of striped bass. The season for eggs and larvae generally takes place from day of year 120 to 190. And for American shad, their spawning season is about 20 days earlier than striped bass spawning season. And for white perch, their spawning season is kind of in between American shad and striped bass. So generally, the survey started in March, which could cover the spawning seasons for the three species. But in some years, the survey started in May, which could have missed part of the spawning season for American shad and white perch. And in some years, the survey ended earlier, which could miss the season for post-toxic larvae. Now let's look at the sampling location effects. The striped bass eggs are most abundant in between river kilometer 50 to 200. As they grow into larval stages, they shift downriver. As we saw in the previous slide, in early years, the sampling intensity was higher in between river kilometer 50 to 150 because striped bass are here. American shad and white perch, they distribute in the upper Hudson in between river kilometer 150 to 245. But the sampling intensity was lower in this area. So this is what happened to shad. These are American shad eggs observations. The x-axis is day of year and y-axis is river kilometer. So these are the missed spawning season we were talking about, and these are the missed survey areas in early years. And these are American shad post-Yoxeclava observations. These are the missed seasons and sampling areas for them. In the previous slide, we say the survey switched from daytime sampling to nighttime sampling to decrease the gear avoidance by post-Yoxeclava. So we evaluate sampling time effects. For striped bass, the catch rates on eggs and Yoxeclava are higher in daytime. When the post-Yoxeclava appeared, the survey switched from daytime to nighttime. So the catch rates on post-Yoxeclava are higher at nighttime. For shad and white perch, the catch rates on eggs and Yoxeclava are still higher in daytime. But for post-Yoxeclava, even if the survey switched from daytime to nighttime, the catch rates on post-Yoxeclava are slightly higher in daytime. And next, we evaluate gear effects. So in general, the catch rates on the epibenthics that had much higher catch rates on eggs for the three species. As they grow into larval stages, they became more likely being caught by top patrol. The gear catch rates are likely related to depth, so we evaluate sampling depth effects. For striped bass, the catch rates on eggs are higher in between depth 20 to 40 meters. As they grow into larval stages, they move to shallower water. And the American shad and white perch, they are generally in shallower water compared to striped bass. Although it looks like they have a wide depth distribution, actually there are not many observations at depth deeper than 20 meters. So these are striped bass egg observations. The x-axis is river kilometer and y-axis is depth. The red lines indicate 20 meters. So it shows that there are not many observations at depth deeper than 20 meters, and most of them are from early years. And it's the same for American shad and white perch. So the uncertainties of estimates at depth deeper than 20 meters are quite high. So these are sampling effects. And with the models we developed, we are able to hindcast the catch rates for the missed spawning season and missed survey area. So here I'm using the American shad eggs as an example. The x-axis is day of year and the y-axis is sampling time. So it shows that the American shad spawning season generally takes place from day of year 110 to day of year 150. And spawning activity could occur over day and night, but it's more likely to occur during daytime because catch rates on eggs are higher in daytime. And we can also use the model to hindcast horizontal and vertical distributions. The x-axis is river kilometer and y-axis is depth. So it shows that the area of river kilometer 200 is a very important spawning habitat for American shad. When their abundance is high and population is big, they expand their distribution toward downriver and to deeper depth. When the abundance is low and population is small, they remain in the area of river kilometer 200. And finally, we compared the model-based and design-based abundance indices. So the top three panels are the eggs abundance indices for the three species. And generally, the correlations between design-based and model-based abundance indices are all statistically significant. But some of them are highly correlated, some of them are just fairly correlated. There are multiple reasons that could affect the design-based abundance indices, such as the missed survey areas, missed spawning seasons, and sampling time. So we saw the peak season effect. Assuming the survey started in the beginning of the striped bass spawning season, the survey could miss part of the spawning season for American shad and white perch. After 3 weeks of daytime sampling, the survey switched to nighttime sampling. So the daytime and nighttime catch rates on each life stage matter. In summary, we saw that the inconsistent sampling design could result in biased estimates of abundance indices. Although the design-based and model-based abundance indices are significantly correlated, model-based abundance indices should be used because they account for sampling effects. And the results of our study can be used to make recommendations on optimizing sampling design and can also be used to hindcast estimates for the missed sampling area as time and space in the past. And with that, we would like to thank the Hudson River Foundation for funding, and we thank the Stony Brook University and the New York Chapter FS. And thank you.